Hi, Dr. Huckabee here. This is another lecture from last semester. This is on chapter 6, starting with enthalpy and thinking about bond dissociation energies. So without further ado, here is your to-do list. So your to-do list is to do your homework assignment and start reading chapter 6 and working the chapter 6 problems. Very important to prepare you for the exam, and the best of luck to all of you. All right, welcome everybody to Tuesday's lecture. In the back, yeah? All right, good. That was a quick yes. That's good to hear. Okay, so before we get started with anything else, we have silly meme time. And you can see here, this is probably one of my favorite chemistry memes that I've ever seen just like randomly pop up on the internet. Some person cleverly saw a picture of Samuel L. Jackson, made the mirror image of it in Photoshop or something, and called that Samuel D. Jackson, which is awesome because these two pictures are enantiomers of each other. Yes. And for the thing to think about today, because you guys are in organic chemistry, you can think about really complex subjects now. Maybe you didn't realize it. We talked a little bit about it with the ocean acidification slide from a few lectures back. But the question remains, why does food smell good and brown when it's cooked? Like, it happens. We love it. Barbecues are awesome. But why does that happen? There's a reason for it. Yeah, exactly. It's the Maillard reaction. That's exactly right. I heard somebody saying it. Essentially, in a Maillard reaction, you have a sugar here on the top with some amines that you find very conveniently in proteins and other good nutritional parts of your food. With some water and heat, you'll condense them to make what's called a glycosylamine or glycosylamine. And once you've made a glycosylamine with a little extra heat, you can start making some really fun compounds like this amidori compound, which eventually, with more heat and time, start making stuff like hydroxymethylfurfural, which has a smell and a taste. And eventually, after some point in time in your pan or in your oven, you start to make these much more complex molecules that have very distinct smells and very distinct tastes. And the construction of all these together is what gives random foods their distinctive odors and flavors that we all love. Really just a very vague explanation of cooking, but there's a ton of literature out there on exactly what happens in cooking, and especially how that pertains to stuff like making beer, meats, and like the best way to marinate meats, in addition to how to make the perfect cup of coffee. So a lot of really cool chemistry out there if you like foods or just learning weird chemistry knowledge. And we mentioned to start this class that we're going to be talking, or start this chapter, we're going to be talking about thermodynamics, and more specifically enthalpy, or heats. And there's a lot of different ways you can talk about enthalpy, which is, or enthalpy, however you want to say it, which is H. And we would call a heat of reaction, or a change in heat of reaction, delta H degree, which just stands for the heat of, the change in heat of a reaction. And there are two different ways we can describe enthalpy and how that relates to reactions. That is either endothermic or exothermic. And so endothermic, I'm putting it in blue because that means the heat increase is in the system. And exothermic means as far as what the book is talking about, the heat is increased for the surroundings. Now, this is a very confusing set of definitions because we haven't talked about system and surroundings at all. So let me give you a brief overview again of an idea of chemistry as a foreign language. Not organic chemistry, this is just chemistry as a foreign language. Because a lot in this course we've been talking about communication, right? And all of us being on the same page as far as what we're referencing and what it is specifically that we're talking about. Because enthalpy is a subjective, it's a, yes? Yeah, I did. Thank you very much. I meant to write surroundings. Good call. Great. It's totally subjective because you're only describing what the heat is doing in reference to your subject. So this means if we're talking about this Kleenex box and I set it on fire, that is an endothermic reaction because the system is getting set on fire. Now see, that's how confusing it is. Is that right? It's going to give off heat if we burn it. So the surroundings will increase. The system will go to a thermodynamic minimum. So actually that will be an exothermic reaction. If you were to talk about the room when this is being set on fire, that would be endothermic. So this is why it's very confusing and for us to set one rule or to have a very clear set of understandings when we're talking about enthalpy and thermodynamics. So what we're going to do is say this. Every single time we talk about enthalpy or entropy, let's leave it at enthalpy. For enthalpy, we're going to talk about the reaction we're doing. So everything is going to be concerned with the reaction. So if we say something is exothermic, that means the thing we're talking about is losing energy, getting more stable. Why? Because we're giving it to the surroundings, but that's what we're talking about. This thing in reference is losing energy, exothermic, which is why it's red. Red has a negative connotation, a warmer connotation, so it makes you think of fire. Exothermic. Endothermic is like ice melting. You have to put heat into ice to melt it, right? That's an example of a thing, a system that is being raised in heat, and that's what you're observing. Very long-winded way to say it. A better way to say it is to just draw out what I'm talking about. So if you plot energy versus a reaction, no, my marker's dying. It's fine, I have another one. Yes. If you plot energy, which is always increasing, going up, versus a reaction, we can plot it two different ways. Assuming that our reactants have the same energy, we can either have a reaction that ends in products that are less stable or products that are more stable or have less energy. And the difference between where these end up, or where they started with the reactants here, and where they end, tells us if they are exothermic or endothermic. If they end higher than where they began, that's an endothermic reaction. I should write it in blue. There we go. That's less confusing. Endothermic. And if they end lower, that is exothermic, because they either gained or lost heat. Yeah, that's these are all definitions. It's kind of difficult to give some nice snazzy examples unless I just set this Kleenex box on fire anyway. That would be a lot more exciting. No, this is the definitions of these things we're talking about. It is what it is. We can calculate the standard energy, the standard change in energy of a reaction, the delta H degree, or whatever this thing is, by using tables like the BDE tables shown up here. Basically, if you don't have a table telling you what the standard numbers are, you can't really figure out how much energy you're gaining or losing, because it's really difficult to collect this data and have it be very accurate. So typically for a reaction, like a really easy one, say for instance, if you have ethane. Oh no, so bad. Okay, let's try it again. If you have ethane, there we are, and you add iodine, and you get ethyl iodide, plus hydroiodic acid, that would be a reaction that is simple enough for you to look up bond dissociation energy values and figure out what the overall heat of a reaction is. And it is actually really simple. Because you have that nice table, all you do is say, okay, the products have some energy, or sorry, the reactants have some energy, and we'll give those blue for positive values. So we'll say, it looks like we're going to end up breaking a CH bond on this ethane. So we just go to our table and we find where the CH bond in ethane is. Where is that? It looks like it is here? Here? Is that right? 423. Okay, so that's 423 kilojoules per mole. I like kilojoules per mole. It makes a lot more sense, but that's because I like SI units. And we find where the CH bond in ethane is. Where is that? It looks like it is here? Here? Is that right? 423. Okay, so that's 423 kilojoules per mole. I like kilojoules per mole. It makes a lot more sense, but that's because I like SI units. So plus 423 for this guy. It looks like it is, what, 234? Is that right? Hard to see down here. 224? Yeah, yes, no? 220, can you read it? It's pretty hard, I guess. 224, okay. 224. 214? How wrong am I? Oh no. Oh man, it is 214. Oh, I gotta get my eyes checked. Plus 214, which is really sad when you have glasses on, right? Okay, so then we also need to form these bonds. So ethane with I. So we go to find ethane with I, and it looks like it's here? Yeah. So that looks like a 235. And when you form bonds, you gain, or the energy is negative. Because remember, you want your energy to be as low as possible. So we're talking about breaking bonds, that's a penalty. You go up in energy, and we don't want that. So those are positive. Forming bonds, you go down in energy to make it more stable. That's negative, and that's what you want. So forming a bond here, negative 214. Negative 214. All right, and then for the HI, forming that bond is 298. So minus 298. And then essentially, once you have the numbers, you just compare one and the other. So let's add these two together to give us, let's see, oh no, 214. Oh, it must be 530. Totally is. It's a little early though. And how nice that whenever the lights go out, there's still sunlight outside. I love that. Okay, so if we do some simple math here, 736 total. And the other guy is what? So 298. So this is 2, carry the 1. All right. Second one. It feels a lot better knowing that they come off, that they go off at 5:30. You know, it doesn't feel quite as annoying. So carry the 1, that's 11. Put the 1 up there, that's 5. Okay, so then once you have the two combined, you just subtract one from the other, because this is minus 512 now, to leave you with what looks like an overall 5 to 125 kilojoules per mole. That's a positive number, which means this is an endothermic reaction. All right, does everybody get how we did that? This is just about literally the easiest thing that you can do. Look up some values. All you really have to know is which one should be positive and which one should be negative. That's all you have to really know. And essentially for enthalpies, just thinking about it, that's about all we can talk about. Look them up in a table, do the math. That's about it. Because we know the most important thing is to be thinking about whether they are endothermic or exothermic.